Moving on, another way is to describe the mole fraction of a particular component. So where you calculate the number of moles of the component divided by the total number of moles of all components in the solution. So this often is represented by letter X, and you say XA. Let's say you have a binary solution of components A and B, and so XA is going to be number of moles of A divided by Na plus Nb in case of binary solutions. Binary solution A and B. So if you had, let's say, n components in the solution and you're looking at the ith component mole fraction, so then you will say number of components of that component I divided by number of moles of that component I divided by, let's say you had n1 plus n2 plus n3, how many ever components you had in there. If you add up all the mole fractions of all the components, you're gonna get 1. For binary solution, you have xa plus xb is going to be equal to 1, and similarly if you add up x1 plus x2 plus x3 for how many ever components they are, you can say that is equal to 1. So this way of representing concentrations is generally is useful when you're talking about physical properties, and we'll look at that in our later videos. When you're talking about vapor pressure, for example, and you're trying to relate it to the concentration of the particular component in the solution, in those cases, this mole fraction comes really handy. It also comes handy when you have gaseous solutions, gaseous mixtures. Next, we have molarity. So molarity is number of moles of the solute divided by the volume of the solution. So you'll see that molarity is used very extensively in chemistry, especially dealing with solutions that involve acids dissolved in water or bases dissolved in water, where you're trying to compare two different acids, comparing number of moles of a certain acid dissolved in a solvent. You get an idea of the H plus ion concentration, and you get an idea of OH minus ion concentration. So in cases like that, this should be in liter here. So when you say, for example, 0.1 molar in AOH, what it means in water is 0.1 moles of NaOH dissolved in 1 liter of water or 1 liter of solution. And finally, we have molality, and this is denoted by small m, and this was capital M. Molarity was capital M. So in this case, this is number of moles of the solute divided by mass of the solvent in kgs. So here it's no longer solution, but it's a solvent. So one point to note here is, if you look at molality or mass percentage or mole fraction, these units are not going to be dependent on the temperature, because mass doesn't change with temperature, or number of moles doesn't change with temperature. What changes with temperature is the volume, because a solution can become less dense with increase in temperature, so the volume can go up. So your molarity is going to change with temperature, and you can get Arrhenius values. So concentration is still the same, but since the volume is different, the value, the numerical value for molarity will change. So in cases like that, we are better off going with something like molality. So we'll look at many examples, and we'll solve a range of problems that'll sort of make it more clear to understand why we have so many different ways of representing concentrations, and what ways are suitable for what scenarios and things like that.